you would see that I have not written anything for the Cartesian subtangent subnormal. Okay, subtangent is y divided by y sub 1. Now let's move to the subnormal. Same diagram. We rub out this part because now we are moving to the subnormal, and I am removing this because I have written it and captured it there. So y divided by y sub 1. This point was in. This is the x-axis. Get back to the same diagram. What we see is, if Qn, this is the subnormal by definition. So as TQ or QT was a subtangent, by definition, subnormal is equal to Qn. Now let's make a few observations. If this is psi, then this is 90 minus psi. And if this is 90 minus psi and this whole thing is 90, then evidently this angle is also psi. There's nothing to go through once again, but I still do, at the cost of earning a bit of displeasure, that if this is psi, and if this is 90, and if this is a right angle triangle, this being 90, then this is 90 minus psi, and this complete angle being a right angle, this angle that I have drawn with two lines here is also psi. So from here we can see that Qn, which is the subnormal, over y, now Qn over y is. Who would disagree that the Qn over y is not tan of psi? It is. Qn over y is tan of psi. So our friend Qn is equal to y tan psi is dy dx. There we are. So one is y divided by y sub 1, and the other is, this we can write as y sub 1. So subnormal we write as y into y sub 1. So these two results must be remembered as far as Cartesian coordinates are concerned. Now, we have appreciated that the length of the subtangent and the subnormal, they depend on the position of P, and of course depend on the slope, because position of a P at a particular point on the curve defines a particular slope immediately. Now, to understand the subtangent subnormal, we have to keep in our mind that it is respectively the distance from the foot of the perpendicular on the x-axis to the point of intersection of the tangent on the x-axis and to the normal on the x-axis. This is the way to remember. It's not difficult. You just have to look at it 2 or 3 times and then the concept gets down our head. Now the question is, can we go to polar coordinates? There are very similar derivations which I do not want to go through in detail, but let me make a statement. Without proof. I am making this statement without proof. In polar coordinates, that is r theta coordinates, The concepts are essentially the same. So what we will do is we will draw an arbitrary polar curve and see how the subtangent and subnormals are. Okay? We just have an introductory diagram, and then we will believe that the polar subtangent is r square d theta dr, and the polar subnormal is dr d theta. That we have to believe. Any good book, for example, the book by B.S. Grewal, Engineering Mathematics, Higher Engineering Mathematics, gives it. Joseph Edwards gives it. Das and Mukherjee gives it. All these are available in very standard and good calculus books. The diagrams are indeed self-explanatory. Now, getting to a diagram. All of us know that in the polar coordinate system there is no x-axis, but there is a line which is normally taken as horizontal, and this is called the initial line. There is something called a pole. That is a point in the plane, and from that point a straight line is drawn in any direction. That is called the initial line. So this is the pole, starting point or a reference point, and a straight line drawn in any direction. Normally, for better understanding, in books, lectures, classes, we take a horizontal line to be the initial line. It could have been something like this. There is no y-axis, but it is always good to have a imaginary y-axis, which in polar coordinates is not necessary. Now, if we take a curve like this, any point on the curve P has coordinates r, theta. We still draw a normal This is the perpendicular P, Q. We again draw the tangent at P and call this Q, T, and a normal like this. So again, this angle is 90 degrees. Does not look like it, but it is 90 degrees. This is theta. This is r. So that is the r theta of this point. As before, we can call this psi. And of course, it is only a question of transforming from Cartesian to polar coordinates or reasoning from first principles. We can capture these two relationships, that the subtangent is r square, so q t representing subtangent can be shown to be equal to r square d theta dr. And q to the, this point is n, qn, which is the subnormal, is equal to dr by d theta. Again, it is a point by point phenomenon. Depending on what is the value of r and what is the value of theta, we get values of dr, d theta, and so on. So these two have to be remembered. One is this box and the other is this block, or rather this block, because this is the initial line. Fine, it's not part of the block. So having said that, we will do a little bit of talking about how to find equations of tangents and normals in Cartesian curves and polar curves and so on. Now, we've done a bit of this in class 11, 12 calculus courses. I need to rub out a bit of the board, and then let's see how differential equations are formed and applied to these things. Let's rub this out. Supposing we want to find for a particular curve the equation of the tangent at this point P. P has coordinates x naught, comma, y naught. So question is, what is the equation of the tangent at x naught, y naught? Equation of the tangent evidently drawn at P, which has coordinates x naught, y naught. On the curve, there. Now here I must mention one very small point, but it might become a very large point. When students are given this problem, there was a point of time I used to give a problem on something like find the tangent to this curve, equation given, at this point, say x naught, y naught, or x1, y1. And purposely, I would take a point that is not on the curve. In other words, I would do something like this. Find the equation of the tangent to the curve C at this point P. This point does not lie on C. Intentionally, we do it. We do it means I used to do it. So, what would happen is, for the students it was a very simple problem, and they would just stare at me and say, why are you giving us this problem at class 12 or class 11? Because most of them come with these kind of problems in class 10. So, the equation actually is y minus y naught is slope dy dx evaluated at x naught, y naught into x minus x naught. Y minus y1 is m into x minus x1, that all of us know. And the normal would be y minus y naught is equal to minus 1 over dy dx at x naught, y naught into x minus x naught. These things we know. Now, by substituting, one would get the equation of a straight line. And now starts the fun. The fun starts now. I would say, are you all right? Do you think your answer is all right? Yes, sir. Take a check. Class 6 algebra or class 7 algebra, I don't want to check. Check it yourself and tell me whether it's right or wrong. All the students would say, yes, it's right. It's not a problem. So I would make them pull out a graph sheet, pull out a graph paper and plot this curve, a few points, standard curves, plot a few points and draw the straight line that you've got. And then it would strike their minds that the point through which the tangent is required, that point does not lie on that curve. So, in fact, I learned this from a question paper of one school many years back, one institution. They had given the question erroneously, wrongly. That means the point chosen for the tangency, for the tangent was not on the curve. And one of my students had answered, this point does not lie on the curve. So no answer is possible, and he got the full 6 marks. The others had done it just by rote without recognizing that. So he had done the right thing. We substitute the coordinates into the equation of the curve and see whether there is an identical truth emerging or not. That is the way to check whether a particular point x0, y0 is on a curve. We substitute the coordinates x0, y0 into the equation of the curve and see if we have a truthful situation or not. But that is not the focus of the discussion. Now, this is the equation of the tangent. We must remember, because sometimes we can link differential equations to tangents and normals. And equation, this is of tangent, and the equation of the normal at x0, y0 to the curve. Let's see, equation of the normal at P on the curve C. On the curve C is nothing but y minus y0 is not dy dx at x0 y0, but minus 1 over dy dx, because the tangent and normal have slopes that are reciprocals of each other and have a different sign, negative sign. In other words, all we are saying is m1, m2 is minus 1. This we have learned for perpendicular lines. So y minus y0 is minus 1 over dy dx x0 y0 into x minus x0. These are not difficult at all. Now, we wish to do one small problem. Let's see how differential equations are invoked into these discussions. So we just pick out a problem and do it together so that the understanding firms up